GATE 2022 rate process questions. In fluid flow, the dimensionless number that describes the transition from laminar to turbulent flow is Reynolds number, Schmidt number, Biot number, Prandtl number. Reynolds number. The dimensionless number which describes the transition from laminar to turbulent flow is Reynolds number, and Reynolds number is relatively low. The flow tends to be laminar with smooth and orderly layers of fluid moving parallel to each other. As the Reynolds number increases, the flow transitions to turbulent flow. Okay. And for a pipe, inside a pipe, if RE is less than 2000, it is laminar, and greater than 2000, it is turbulent. And for an external flow such as over a plate, the RE is nearly greater than 5000. 5000 to 1 lakh also, 10 power 5. A Newtonian compressible fluid or liquid is contained between two parallel plates and metal plates separated by distance 10 power minus 3. And now a stress of 5 pascals is applied, required to maintain the upper part in motion with constant speed of 2 meters per second in the horizontal direction relative to the bottom plate. The viscosity of the liquid contained between the plates is dash into 10 power minus 3 Pascal seconds. This is the plate 1 and plate 2, and this is the liquid between. The height of the liquid is 10 power minus 3. Now we know shear stress tau is equal to mu into du by dy. Okay, Rn is the dynamic viscosity and du by dy is the velocity gradient between the plates. It is given that the upper plate is moving with a constant speed of 2 meters per second and separation is of 10 power minus 3. So separation is 10 power minus 3 and du is equal to 2 meters per second. So we can calculate, and also given the shear stress is 5 pascals maintained such that the upper plate is in motion at a constant speed. And now we need to calculate the viscosity. So 5 is equal to viscosity into 2 by 10 power minus 3. So mu is equal to 2.5 into 10 power minus 3 Pascal second. So answer is 2.5. So which of the following is true regarding the black body radiation? Among all the radiations emitted by the ideal black body at room temperature, the most intense radiation falls in the visible light spectrum. The total emissive power, see, among all the radiations which is emitted by the black body at room temperature, the most intense radiation doesn't fall in the visible spectrum. And also, the total emissive power of an ideal black body is proportional to square. No, it is proportional to T power 4 of the absolute temperature. The emissive power of an ideal black body peaks at wavelength lambda, which is inversely proportional to absolute temperature. Yes, according to Wien's displacement law, lambda T is constant. This is right. The radiant energy emitted by black body is greater than that emitted by non-black body at all the temperatures above 0 Kelvin. This is also true. So let's see. The emissive power of a black body is inversely proportional. Yes, according to Wien displacement law, the wavelength is at which the spectral radiance of a black body curve is inversely proportional to absolute temperature. And as the temperature of the black body increases, the peak of its emission spectrum shifts towards the shorter wavelengths. That is why the hotter objects like stars or very hot objects emit more intense radiations in the blue and violet range, which is cooler objects emits in the infrared range. This behavior is consistent in the nature itself. The radiant energy emitted by the black body is greater than the non-black body at all temperatures. generally the black body is defined as an object that absorbs all the incident radiation and emits the radiation with maximum possible efficiency. Among all the radiations emitted by the black body, the most intense radiation does not fall in the visible spectrum because the distribution of the radiation emitted by an ideal black body depends on its temperature and it follows the curve known as black body radiation curve. The peak which the most intense radiation lies is shift towards the shortest wavelength as the temperature towards the longer wavelength and temperature decreases. At room temperature, the peak of the black body radiation curves fall within the infrared range. As the temperature is increasing, it moves towards shorter wavelengths. So it is not in the visible range spectrum. Okay. Thank you. Now, a non-rotating smooth body, a solid spherical object, is fixed in the stream of inviscid incompressible fluid. So the horizontal flow, slow, steady, and fully developed far from the object as shown by the streamline arrow near the point O. Which of the following is true regarding it? If you'll see, the velocity of the fluid at point A is 0. This is true. Because there is no slip condition that at the solid boundary, the fluid particles is in direct contact and sticks to the surface. So they have the same velocity at the surface. As the surface itself is at 0, the fluid velocity at point A also becomes 0. So it gets stuck to the surface and moves with it. The fluid particle move away from the surface. Now, if you'll see, the fluid at point A exceeds that at point O by an amount of half rho v square. So if flow Bernoulli's principle, fluid at O plus half rho v square, rho 1 square is equal to PA plus half rho VA square. As this is 0, it approaches 0. So the pressure at this point is exceeding the P naught by half rho v square. And also, so this is also true. On each side of the central streamline of O, the flow will be deflected around the object. The statement is also true because as a fluid approaches the object from each side, the fluid path is a fundamental behavior in fluid dynamics. So what will happen is the occurrence of the interaction between the fluid and the object, the deflection leads to the formation of curved streamline around the object. So along the fluid to smoothly flow past it. Now coming to option C, the fluid moving precisely along the OA will turn perpendicular to OA and to circumvent the object. No, it does not turn perpendicular. Instead of it, it gets moves along the surface smoothly and then follows the path. Because the particle moves along the streamline without crossing over the streamlines. This ensure because see if this is a streamline, the particle will never cross any other streamline. It follows only its streamline path and goes in the streamline itself. When the fluid encounters the object along OA, it will start to curve the object surface due to no slip conditions and the influence of pressure gradients. However, fluid will not turn sharply and abruptly perpendicular to OA. Instead, it will follow the curvature path of the object and smoothly circumvent the object. This is an important question which covers a lot of concept. Okay. The spherical gas bubble of radius 0.001 millimeter is entrapped in molten steel held at 1773 Kelvin. If the pressure outside the bubble is 1.5 bar, the pressure inside the bubble is dash bars. So we know 1 bar is equal to 10 power 5 pascals. To find the pressure inside a gas bubble entrapped in a molten steel, you should know, like, if this is gas bubble and outside it is full of other fluid, then P inside minus P outside is equal to 2T by R. If this is gas bubble and outside also it is air bubble, and this is gas bubble and the layer is also formed by an air, then P in minus P out is equal to 4T by R. So here if you'll see, this is applicable. So P in is the pressure outside the bubble and pressure inside. Pressure inside we need to find. Pressure outside is 1.5 bar plus 2 into 1.4 Newton per meter by 0.01 into 10 power minus 3. Okay. So it is 1.5 into plus 2.4 is 2.8 into 10 power 5 Newton per meter square, which is Pascal by 101325, which is almost equal to 2.8. So it is 1.5 plus 2.8, 4.5 atmosphere or bar. Sorry, 4.3. 1.5 plus 2.8. The rectangular block made of material 1 and material 2 are identical cross-sectional, has a temperature of T. So the temperature of 435 and 400 at bottom and top surfaces respectively. The assuming purely steady state conductive heat transfer, the temperature at the interface is, so this temperature we need to find. So we know Faraday's law, which is K1 A1 delta T1 by L1 equal to K2 A2 delta T2 by L2, which is equal to, as L1 and A1 is same, K1 delta T1 equal to K2 delta T2. So this is given as 50 into 435 minus T is equal to K2 is given as 200 into T minus 400, which is equal to 4 times. So 435 minus T is equal to 1600 plus 40. So it is 2035 is equal to 5T. So T is equal to 2035 by 5, which is equal to 407 Kelvin. So the temperature is 407 Kelvin. The air at 300 Kelvin passed as a mass flow rate of 1.5 kg per second through the metallic tube of inner diameter 0.08. The inner wall temperature of the tube is maintained at 700 Kelvin. The temperature of the air leaving the tube is 600 Kelvin, assuming that the heat transfer occurs entirely by the steady state convection. The length of the tube is dash. So, applying energy of conservation of energy, we know the convective heat transfer is HA into T minus T and MC dt by dt. This is equal to MC dt by dt due to mass flow rate. So the HA integral dt is equal to m dot C into dt by integral T minus T infinite. So this is equal to H into pi into D into L into time T is equal to m is 1.5 into 1080 into ln T infinite is given as 700 Kelvin. So it is 700 minus T by 700 minus 300. And the temperature is ranges from 300 to 700. So now so uh, you got here like heat transfer T infinite minus T is m dot C. Then see, you should remember a concept here called the inner wall temperature is maintained at 700 Kelvin. Now the air is coming at entering at 300 Kelvin, but leaving at 700. So the wall is maintained at this temperature. If the air is entering at 300 Kelvin and it leaves at 600 Kelvin. So the difference in temperature is 100. Here it is 400. Now it is minus m dot C ln T minus T infinite. If you'll apply it from 100 to 400 and T infinite is 700. I have already applied the difference. It is m dot C ln which is 400 by 100 is 4. Okay, this is equal to H is given as, so into ln 4. H is given as 500 into 3.14 into L and m dot. So I have transferred this to here, which is equal to 1.5 into 1080 into ln 4. So if you'll calculate, you'll get, and the diameter I forgot to mention, it is 0.08 meters. So you'll get L as, if you'll calculate 1.5 into 1080 into ln 4 divided by 500 divided by 3.14 divided by 0.08, which you get as 17.88 meters. Okay, thank you.